the ARMA hydraulic fracturing community rope talk series, and this is the 8th. Amazing. We finished the month of April. Now we're going to the May, and some of the cities start relaxing the strict stay-at-home rules, including Houston. And but we still need to be very cautious, especially not only for ourselves but for the people around us, for the health, well-being. I just share this safety moment as face mask seems become more and more accepted now in the companies and the countries. Yeah, I just mentioned this to one of my colleagues this morning, that we wear face masks not only for ourselves, it's also for people around us, especially our colleagues and family members. Nevertheless, today is our great pleasure to welcome one of great speakers from Rockfield, Adam Bere. He actually, I knew him for a while. He is growing up in Swansea, educated in Swansea. He is, except nowadays he started a new look, but nevertheless, he has been tremendously helping Rockfields grow the company, grow the technology, is CTO, Chief Technology Officer, as well as a Director for consulting projects. He also leading some of the GIP's research projects at the company. And like I said, he graduated from university in Swansea all the time, from bachelor to PhD. Before I turn over the mic to Adam, a couple of house cleaning items, especially for the folks who are new to this Rope Talk series. Welcome on board, first of all. Second, this is the Carol Technical Talks, so no recording or photo taking, but we don't ask presenters to release any material, but over the past, many of them actually have generously released their presentations as well as the recorded videos. So today, thanks Adam, and thanks for our host, Andy Bunger from University of Pittsburgh again. This presentation is going to be released as well as the video recorded. So you don't need to do anything, just enjoy the talk. That's the first thing. Second, mute yourself to avoid echo. And if you have questions, please type into the chat window, and Adam will address them either within the time frame of this Rope Talk or follow up with emails. The Rope Talk series lasts about 45 minutes with 30 minutes of presentation and 15 minutes Q&A. Normally, we stop at 45 minutes, but in case the host is available, the Zoom meeting can extend longer, so the presenters like Adam can stay on and answer more questions in the chat room. So with that, Adam, feel free to take over. Thank you very much, Adam.
Great. Thank you very much, gang, for the introduction. Hello, everyone. Hopefully you can see the screen. We had a quick test before, so hopefully it's up. Many thanks as well for the organising committee for giving this opportunity. It's fantastic at this time that we can do this and share the insights that we've seen in the hydraulic fracturing technology space. Let me get this presentation working. Okay, so contents. What I'll be talking about today other than the title, which describes the basis of it, stress shadowing. But I'll go through some background observations and motivation for why we're presenting this, why we're trying to show the technology and the reasons for stress shadowing and potential rotation of fractures. Secondly, then we'll go into the state-of-the-art modeling, what's out there now, what can capture these different aspects in the subsurface, what's important there. We can look at that in a single fracture stress shadowing aspect to get the basics out there, the understanding of what controls it, then developing into a 3-cluster stress shadowing model. Then we can look at a multi-cluster model. So this is something that's possibly more familiar with multi-cluster fracture jobs. What are the implications on the fracture patterns that are seen there? And then conclusions and final future work potentially after this, and obviously Q&A session then. Feel free, I've got the actual chat screen up here, so if there are questions on specific slides, feel free to put in the chat there. I'll try and keep an eye on it and answer it as we go along as well. So looking at some of the background motivation observations, as I mentioned, stress shadowing's been known for quite a number of years. Lab scale tests have picked up complex fracture patterns that are derived from these stress shadows, where potentially dominant fractures are propagating and actually reducing the propensity of other fractures, other clusters to propagate, or changing the orientation of them. So there's a lot of interaction there, potential branching, choking, curving of these fractures as well. So there's some nice lab scale tests shown there on the left back from 1999, and then some model results there on the right, just to give a flavor of the things that could be seen here and why there's a bit of motivation for looking at it. Other lab scale tests that have been seen here as well. Here's a nice example here, again going back quite a few years now, demonstrating this stress shadowing and potential complete shutting off of certain clusters in growing. This pattern that you're seeing here is complex and has major implications for where the actual propagating fractures will go, which then has implications for productivity of a certain field as well. When we look at the field scale, these observations are also seen here. So here's a couple of examples of different stages that are run through. On the left side there, we're looking at the amount of production that is actually seen, and the majority of production is taken from 70% of the clusters or the perforation clusters that have been set off there. 50% of them is showing virtually no production. So there's a question as to what this is due to. Is it due to the heterogeneity in the formation itself, or is it potentially due to stress shadowing and actually some of those fractures not propagating at all? As you can see on the right-hand side there, this is a known function where there's sort of waves of fractures as they propagate, where the stress shadowing builds up and then actually starts reducing. This is something that's been seen in many different publications as well. So not only seen in lab scale, but also seen in field scale. Here's a really nice demonstration from acoustic measurements taken, so with respect to time going across the x-axis here. You can see the current stage and where it's located. What's actually observed here is outside of that current stage is the extent of a stress shadow. From the acoustics, it can be diagnostics from there, it can pick up where the stresses are actually changing and how far away from there. A question comes up as well, talking about stress shadowing in the near wellbore. That's an ideal question, and I agree there is stress shadowing even at that level there. The focus of this one at the moment is looking more into the further field. However, right at the end of the presentation, I will show you something that is looking more at the local wellbore scale as well. So you can see even under injection, when the pumps are shut and relaxation, you can see the fractures closing, you can see relaxation of this stress shadow. So this is the current stage. You can see how it's affected the previous stage, potentially will affect future stages as well. How are these looked at the moment? How do we account for stress shadowing? There's a lot of analytical assumptions built in here. semi-infinite fractures, penny-shaped fractures, which can look at the amount of stress shadow into the formation as it's passing through, and change and update those stresses for future fractures propagating. Generally, when it's done analytically, there's big constraints that are put onto these assumptions. There's no or limited heterogeneity of the formation material properties. Competition between propagating fractures isn't really accounted for. It's assuming that a single fracture or a stage, a cluster of fractures will propagate. They'll change the next stage. Adjacent fractures, yeah, you can account for that, but as I said, there's little competition there. So what we look at then is, well, with modeling, how can that take us beyond the analytical assumptions and constraints? Modeling's advancing at a rapid pace. We can look at hydraulic fracturing all the way around actual fractures as they grow. What you can see on the right-hand side there, actually there's a near well bore example there, so quite timely based on that question. You can see multi-perforations propagating there, but where do the actual fractures generate from there? Do they generate from each perforation, or is it some select ones? How much of that can be contributed to stress shadowing? We've got reorientation of the actual stress field there, bringing out a longitudinal fracture there as well. So really, really important questions there. Obviously, understanding the near wellbore, only then can you understand how it's going to go into the far field. As I say, we'll concentrate on the far field in this presentation. What's nicely shown on the left here as well is this is some work which was done out of Imperial University, and they're looking at sort of these petal shapes as well of the fractures, where you can clearly see that stress shadowing and competition between these fractures end up driving the shape of these. So very, very similar to what we're looking at, and what I'll present in this model has been done in other software as well. So it is an emerging technology, but it's being used in multiple different arenas, commercial and academic, which is really bringing it to the forefront. So if we look at where the current state is for modeling, finite element modeling, physics-based, incorporating DFNs, anisotropy, mixed mode failure, layering, laminations. You can have 3D curving fracture planes as well, multi-wells and stages, how they interact with each other. So everything we're starting to list there is really taking us beyond standard conventional analytical assumptions there. And it's taking advantage of modeling that's being used in many different industries for many, many different years. The civil engineering industry has used this kind of modeling for structure-soil interaction as well for quite a number of times. There is certain unique aspects with hydraulic fracturing, particularly looking at the actual injected fluid, how it passes through the fracture to induce that pressure which opens up the fracture in the first place. So that's something that's really important to be captured as well. So if we take a fresh look at this and look at a single fracture and the stress shadowing from a single fracture, we're using this with the Elvin software TGR, so we can look at both the in situ stress, which is applied under the initialization, but then also the evolving stresses. So through the formation, through the whole propagation, whole injection stage, the stresses in the formation are being updated all the way around the fracture, not consistently, but only where it's starting to propagate. That's based on the material properties you have in there, and also the yield properties of the formation. The fracture fluid flow and pressure within the fracture, that's governed by the viscosity of the fluid, the aperture of the fracture. Is there a decline from the pressure from the source, from the well, all the way out to the fracture tip? That can be captured in these kind of models here as well. So bit of the model details here. We're trying to represent something relatively appropriate for subsurface. So the Young's modulus we have in here, 32 gigapascals, tensile strength 7 MPa. We have in situ stress conditions, I think down here, 50 MPa vertical, 40, 42. Pore pressure 30 MPa. And we're injecting 15 barrels a minute. 1,250 barrels to start with. as we go through the modeling, there's a few questions coming up. I'll try and hit them as we hit the appropriate part here as we go through. Some of these hopefully will be answered as we run through. So if we look at single fracture insertion, what criteria are we looking at to insert that fracture? Well, at the fracture tip, there's a stress intensity. To generate the fracture, to insert it, that tensile stress intensity must exceed the current minimum total principal stress and the formation tensile strength. It must overcome both of those to actually fracture the rock. Inherently, the in situ stress state is compressive. You have to overcome that to even go into a tensile region, and then the formation strength. You have a decline of that tensile strength before the fracture is actually inserted, something referred to as the fracture toughness. We use the fracture energy, so it regularizes the size of that fracture that's being inserted. The injected fluid there, where the fracture has been imposed, will still be applying compressional stresses adjacent to that open fracture. That is something really important to look at where the stress field is changing within the formation. So you can see in this diagram here, there's an animation running through, but there's a snapshot here on the bottom right. You can see this light blue color is the in situ stress state, and then you can see this compressive region there, which actually starts propagating further. The stress intensity is going to the red, the hot colors you can see there, and then that will break the rock at that point there. Now, any potential curvature of the fracture that we have here, we don't define the orientation of the fracture. That is governed by the damaged elements ahead of that fracture tip. That in turn is governed by the stress intensity of that fracture tip. If there is a bias to one side or the other, the fracture will turn that way, and numerically we represent that. We don't constrain the orientation of that. At the moment, we are looking in 3D, we're just looking at tensile damage. That's why I've focused on that. Shear damage can be captured in 2D modeling. It's very complex in 3D. That's somewhere we want to take it. But at the moment, we're just concentrating on tensile damage. So that's how it rotates basically from that stress intensity in that area there. So when we look at this next slide, I put in a slide on the Young's modulus. This is a really, really important material parameter for that stress intensity and for the amount of stress shadowing you will see. So two cases we run exactly the same as the previous one. The first one is the 32 gigapascals, as I mentioned. Then we've done a softer formation, 16 gigapascals. Well, you can see if I go across from the left here, you can see left at the bottom, the graph, the injection pressure, very, very similar for both. We have a large injection pressure to start with because we're starting with a very, very small fracture there. Numerically, you've got to break those rocks down. And then quickly it declines to the propagating pressure there. See, it's very, very similar for both of these cases. The reason for that is because the total in situ stress and the tensile strength are the same for both of these cases, even though the Young's modulus is different. What you see in the next graph there is the fractured area that we have. So as you're propagating through, the surface area of that fracture is greater for the 32 gigapascal model. We're injecting the same amount of volume. What we tend to see is the aperture is less for the stiffer rock. The rock isn't compressing as much either side. So if the aperture is not growing as much, you are going to get a larger fracture developing. So you see that in this case here. What we've taken here is a dashed line through the model, through the center of the fracture and perpendicular to the fracture direction to look at this stress shadowing effect, the compressive stress shadow. You can see 32 gigapascal. You can almost see it with the contours. You can see that it's greater in the stiffer rock there. Stiffer rock generally will carry stress further out. The gridding that we use for this is unstructured tetrahedral elements in 3D, triangular elements in 2D. Ahead of the fracture tip, we constantly remesh the head of the fracture tip. So we throw away the previous elements, we populate it with new elements, and we incorporate the geometry of the fracture as it propagates through. That's completely automatically generated there. This is a big step away or apart from reservoir grids, which are very static. They're structured grids generally. We've got completely unstructured. There's two sides to that as well. It introduces a bit of heterogeneity. When you have slightly different shaped elements, they will attract slightly different bits of stress. Actually plays into our benefit that there is heterogeneity in there, because inherently you will have heterogeneity in formations. And that's probably one of the reasons why you see it not perfectly planar there. We can also introduce heterogeneity stochastically into the material properties there, Young's modulus or tensile strength, just to capture a bit less of a rigidly constrained model there. It actually follows a little bit more reality. An example here now, looking at elastic heterogeneity. On the left, you can see the Young's modulus, and this is a vertical 2D section, propagating vertically. So we've got an elevation model, if you like. You can see there's big contrasts in stiffness there. I'll run the animation again. This is the fracturing as it goes through. You can see the stress shadow as well. So red now is more compressive. The purple colors are going more tensile there. So you can see ahead of the fracture tips there, you've got big areas. That stress shadow area is growing. It's quite significant ahead of that fracture tip. And it is also the amount that it's distributed laterally is a function of the stiffness of the rock that you have in there as well. So what we're seeing with these models is the rate of that fracture growth is also a function of the elasticity as well, at how concentrated that stress intensity is at the fracture tip. So that's a quick basics behind single fracture growth now. When we look at 3-cluster growth, so we're looking at this stress shadowing. You can see what it is on an empty domain with a single fracture, but we want to see how the 2 fractures or 3 fractures are going to start interacting, competing, influencing each other because of this stress shadowing. So we got an example 3-cluster model. For this, it's essential modeling wise to consider limited entry perforation. So all completion designs will be done such that as the majority of the clusters can potentially grow, where you penalize clusters or fractures that are taking too much fluid. You can penalize them with the pressure drop between the well pressure and the fracture pressure. That drop in pressure restricts that fracture growing more and allows others to catch up, if you like. There's lots of different technology in here. There's particle diverters, many different things here which can be introduced to actually plug up some of the greedy fractures, if you like. But it's quite important to have this, especially when we're introducing stress shadowing. Otherwise, we will see one dominant fracture growing. So if we look at these animations here, hopefully one more click will get them going. On the left, then, we have no perforation drop. So what you're seeing is you're seeing one dominant fracture starting to overtake. It will induce a marginal stress shadow on the other fractures. You can see right at the beginning, actually, the 2 end ones are starting to propagate. But as they're growing, they will impose this stress shadow. There's unstructured mesh there. It's growing relatively irregularly to follow the heterogeneity in the subsurface. And this one fracture is dominating now. As soon as it starts to grow, the lever arm effect of a larger fracture makes it easier to generate tensile stresses at the fracture tip, or less pressure within there to generate that. So your first fracture that grows large will actually carry on growing with less pressure demand than the other fractures. That's just geometrically, that is true. But then also we have the stress shadowing effect. So as soon as that larger fracture grows and imposes more stress shadowing on the other, they will become shut off as well. So on the left, we're looking at somewhere where there's no limited entry penalty to the fractures. On the right-hand side now, you can see that all of these fractures are growing now. We put in some details of the number of perforations, diameter, and discharge coefficient as well. So, and this is really the interesting thing, because we're starting to see the stress shadowing in these 3 here. Just looking in plan, you can see 2 are propagating one way. The other one's propagating 2 to the east, 1 to the west, if you like. And then vertically, you can see a change here as well. When we saw that imperial model previously, you saw those sort of petals that were growing there. You're seeing that again in this 3 cluster case. So what we'd like to do is just take a step back, cut through the model, and really look at the stresses that are being generated within the formation between these fractures and why we're seeing this growth or preferential direction growing with these. So again, you can see this significant impact on the resulting fractures as they're propagating. Sometimes you see, due to stress shadowing, all 3 fractures propagating symmetrically, but some of them may be a smaller half length, they may be a smaller aperture because of the fracture, but this is actually showing that there is potential for the stress shadowing to actually stop the fractures propagating that way and have that asymmetric growth there. There is a similar size to all of these 3 fractures that have grown, but you can see there's also coalescence between the fractures in terms of the stress as they're building up there as well. So what we can do is take these models back to very, very early propagation stage. This is just 100 seconds into the propagation. We do have a starter fracture in there as well of a certain size. You need that lever arm in there. So we assume we're sort of skipping the near well-bore fracture propagation. We're saying, okay, propagate perpendicular to the well. This is where you're starting. But all of these were initially aligned up together. So this is just 100 seconds in. They've grown to 35 meters total length there, so 17.5 meters half length. Just zooming in here now, looking at those stresses, what we've done is, this is a 3D model. We've just taken a horizontal plane here to plot all the stresses on. So you can see you're getting stress shadowing from all of these models, compressive stress shadowing here. Now, each one of these compressive stress shadow is starting to affect the neighboring fractures. So if we take this case on the top left here, in fact, let me get my pointer out here. Okay, so if we take this case here, this compressive stress here from this fracture is actually keeping the stress at this fracture tip more compressive. We're looking at tensile being the hot colors here. It's got to go tensile to break the rock here. So it's starting to affect this fracture. It's likewise starting to affect this one. These 2 outer fractures then are almost combining and coalescing the fracture and really starting to stop that middle fracture growth there. So this stress shadowing is increasing the in situ stresses in front of the neighboring fractures, placing a greater demand for future fracture propagation. Where's the fracture going to grow? It's going to grow in the path of least resistance. You've got to remember that we are updating the in situ stress all the time through this simulation. So we're not just taking the initial in situ stress. It's constantly being updated. These fractures will then grow the only way that they can. Now, this is just a 2D plane we're looking at, so it's a little bit more simplified. But these can propagate in this one direction you can see here. This is somewhere where there's minimal or no compressive stress shadow, like in this case here. So if I just take this back and, apologies, let me just take it back to here quickly. There's some questions about turning of the model. 1 second. Let me get rid of my pointer. And then I should be able to, okay. I'll go back to here, all right. So what you can see, if you look in these models here, they're not remaining, these fractures aren't remaining planar. They are actually turning in this direction here. Now there's a few things with the turning of the fractures. There is a demand on turning of fractures. It needs more energy than a planar fracture. So they'll only turn where they need to. There's a few other things that govern how much it will turn. The anisotropy of the stress state that you have is a key factor in how much, or the propensity for it turning. Also the stiffness of the rock, going back again to the stress intensity at the fracture tip and any bias for one direction or another. We did do some other work on that previously, probably something for a different conversation there, because it will spill into things on what causes those fractures to turn, what are the key drivers. I just wanted to show that animation again on the bottom right there, showing that we are still seeing turning of these fractures. So if I skip back to where we are looking at a multi-cluster case then. So in this case, we're looking at 11 clusters here with 6 meter spacing. There's questions about the spacing on the other ones. We'll go back to that in a second, but this one's 11 clusters now, 6 meter spacing. You can see just over 5,500 barrels slick water, 80 barrels a minute. The size of the model here, 250 by 250 by 100 meters deep here. We don't really, with the model, this is a single domain here. We can apply vertical heterogeneity in a 1D sense. We can apply 3D heterogeneity. We don't really like to split the model into sections of fracturing and non-fracturing. So we can incorporate the basement, the cap rock in the model as well, and allow that to fracture if it needs to fracture, if the stress state, the material properties, if the injection is such that it will want to break through the cap rock, we can still represent that. If I show this animation, then you'll see what's happening with these 11 clusters here. 6 meter spacing, so you'd expect quite a lot of stress shadowing here. And again, what you're seeing, like we saw before, you're seeing this kind of petal shape where the fractures are sort of shadowing each other, so they're all trying to grow in an area of least resistance. And what ends up is you get this nice spiral petal effect here. As we look through, when we're starting to look at this, what are the implications? What are we actually seeing? So looking in plan view on the top right there, 170 meters straight across, but each fracture is about 100 meters there. So you've got to think about the half length, think about potentials for frac hits. If you've got asymmetric fracture growth because of stress shadowing, are you increasing the likelihood of frac hits to the next well? Height growth as well. So in the picture on the bottom left here, this is looking at the height growth. You've got 90 meters here. Now, if all of these, again, if the fractures were growing to a similar extent, you may not get such extremes in the height growth there. It may be reduced significantly from what we're seeing there. So I think time's looking pretty good at the moment. So what are the implications? I mentioned before frac hits. I just mentioned that now. What is taken as a fracture half length here? Some dimensions of what we saw in that model we've just seen. Fracture height growth growing out of zone. Really, really important. We don't put in any caps to the basement or cap rock. Does stress shadowing put such a demand on fractures that actually they would get enough energy to break into other formations as well, or break through other areas that are typically seen as barriers to the fracture height growth? Stimulated reservoir volume, the surface area of the fractures, where it's actually covering there. Different implications there. Obviously, if you've got natural fractures in place as well, what would happen there? Are there undrained sections of the reservoir because of this stress shadowing? Proppant placement as well. So we can model the placement of proppant. Where this becomes quite interesting is proppant will be carried, it depends at what stage it's put into the injection schedule, but if your larger proppant is put in at a later stage, if your fractures preferentially grow in one direction or another, does that just carry the proppant to certain parts of the fracture rather than evenly distributed across the whole fracture there? Further applications of this kind of modeling work that we're looking here, where there's input for completion design. If you know that you're getting stress shadowing here, can you overcome it by looking at the completions and put in a more aggressive system for particle diverters or penalties there for the pressure there? Cluster stage spacing, at what point do you not see the stress shadowing? Is it appropriate to put them too close together? Is it actually appropriate to put clusters closer together so it naturally finds that spacing and you get that petal effect there? That may be desirable. Well spacing, obvious implications there. Near wellbore fracture stress shadowing. So we've done quite a lot of work previously on this, and there's a couple of snapshots there the near wellbore stress shadowing, where you may have a series of clusters set up, or perforations in a cluster. You inject into that cluster, where are the prominent fractures going to grow? Is it a single fracture? Is it dual fracture? Is it potentially even more, or is it less? The injection fluid viscosity effects, that's a really interesting one. As you put in more viscous fluids, generally you put a higher pressure close to the well. That's going to put more stress shadow impacts across different fractures there. So that's a really, really interesting aspect there. All the modeling you've seen at the moment is just slip water. We can put in different viscosity fluids, and looking at how that affects the stress shadow is quite important. And then 3D heterogeneity I mentioned before, that can be put throughout the model to see how that behaves, a more realistic subsurface characterization. And we're at the end of the presentation there, so thank you very much for your time and attention. I can see there's quite a few chat questions there, so we'll try and go through some of these. Let me see where we are. Okay, so there's some questions about the turning of the fractures, so hopefully I hit some of those questions there on the rotation of the fracture. In situ stress, yeah, turning of the fracture, there's some papers there. Maximum pressure values, fracture lengths. How do they compare with predictions? Yes, so we've done quite a bit of work for different operators. There's obviously only a certain amount of stuff that we can show here. We've had quite a lot of success with that in capturing how many fractures are propagating. There's a case that I can't go into details of, but we may only see a small proportion of the clusters actually propagating, which has a significant impact on what the pressure demands are on the surface, if it's only passing through a limited number of fractures. And we're actually matching that extremely well. If we change the completion design, that can change it considerably in terms of the pressure. So we know that it's due to the completion design and the number of actual running fractures that are giving that pressure response. It's difficult. I wish I could go more into detail there. Unfortunately, we can't too much there. Microseismics, that's a great question. Evidence of the microseismics and asymmetric fracture growth. I may well have cut a slide out which showed those previously. I'm just going back up, but when I was collating this together, I did have one on microseismics. I have taken that out. There is evidence for microseismics, depending how the microseismics are interpreted, but there is evidence that there is asymmetric growth there. A lot of work's been done in diagnosing the microseismics for frac hits to understand the frac hits, and you can see significant asymmetric growth there. Proppant concentrations there as well, how that affects the viscosity of the slurry, absolutely does. So as I mentioned, with the viscosity of the injection fluid, the amount of proppant you've got in there as well, obviously that hand in hand with that becomes the aperture of the fracture there. Obviously the smaller the aperture, the greater the viscosity and proppant impacts become. So that's a great question. I think it will affect things if you get a fracture that's thin enough where they really take precedence there. Yeah, there's a question about the model results and the observations on fiber optics. Okay, I'm not sure what's actually mentioned there, but one thing that is, we're at the Hydraulic Fracturing Technical Conference in the Woodlands, and what's really interesting with all of this is actually erosion of the perforations as well. How much does the erosion of the perforations start affecting the resulting fracture geometry there? Generally, the erosion will come in once the proppant is being injected. So a question comes in is how well defined are the fractures prior to the propant going in if there is no erosion there. As soon as you do get erosion, if you do have dominant fractures, they're only going to become more dominant. Obviously, then particle diverters can come in, but I think the erosion side of it for the perforations is very interesting. We're actually at the point of coding in some erosion models into the pressure drop calculation that we've got in the model, so that will be something we can look at there. Can this be upscaled to multi-well pad with zippering operations? That's a great question. So the modeling we have at the moment, it's pretty detailed. Hopefully you got an appreciation of what we're doing here. We're inserting or extending the fracture all the way around these fractures in 3D. We're having to calculate the stress changes between them and the flow through the fracture. Numerically, it's pretty intensive. We can look at multi-well, multi-stages, but you're talking about, you know, a handful of stages there. When we've had these questions before, we've sort of gone back to, well, it's quite important to first of all understand where a single fracture is going to grow. Then it's important to understand how a stage is going to perform, particularly when you're talking about height growth. When you then look at subsequent stages from there, we can impose stress changes from prior stages and run those through, see how much they're affecting things as well. So to a certain extent, we can look at multi-stages all the way down, but there's certain approximations need to be applied there. Leak off, there's another question about leak off. So we've got many different models for leak off. Constant leak off, we got two-term leak offs. We can incorporate sorry. Yeah, so we've got the ability to actually leak off into the formation as well. So we can change the pore pressure within the formation. So likewise, if there's depletion and then there's refracking, we can represent the stresses changed due to the depletion and the potential implications on refracking there as well. Brief comment on the CPU time needed for these kind of simulations. Yeah, hopefully I highlighted the computational demand on this. Hand in hand with that becomes the run times. The 3 fracture jobs we were looking at there, I think they took about 4 or 5 hours to run. If you're looking at 2D runs, so going through that, let me just get the one up here. So through through the elastic heterogeneity, I mean, I think this one took a lot quicker to run. You're talking about a sort of an hour turnover for this in 2D. It is 2D, so you're at that level. But if you're looking at potential height growth of these fractures, this is a great screening tool for landing depth. We actually did a lot of work for an operator looking at landing depths and where the resulting fracture would propagate. Again, we don't restrict where it grows into the overburden or underburden from the reservoir, and we're actually seeing it growing quite significantly below the target reservoir area there, which help guide where the landing zone should be. A lot of this can be brought in directly from log data, and all the properties transferred straight into the model so it can run through there. So variations of this can be done extremely quickly. I may be losing losing where the questions are. Thanks a lot for the questions. It's far better than a quiet room. Hopefully I've covered a lot of them. Just looking through, there's nothing significant there that I'm seeing, but you know, you can follow up afterwards with other questions and discussions that we can go through. I'll be more than willing to do that. Gang, I'm not sure how we are with time with everyone, but
thanks, Adam. This is a fantastic talk. It's nice talk that open up people's working week on Monday for this week. Good job always. For the folks who are not familiar, we release those talks as well as the meeting invite for next talk in the HFC newsletter. If you have not received any newsletter from me, that means you need to send me an email to get on that email list. My email is gang.han@aramcoamericas.com. Send me email, then you receive those. Thank you, Adam, and feel free to stay longer if you need it, but our official Robe talk ends at 45 minutes. The next